morning. I don't know if I forgot to say this last time. I think I did. Sometimes I do. My name is Per, and I'm going to be the teacher in this course. Last time we had about, here's a single column of data. Maybe there's more than one column, but at least a few columns of data in your, for instance, in your Excel sheet. How can we look at this data? How can we tell the story about this data? By calculating some summary statistics and by doing some plotting. As I said, this is an exercise looking at data that we started like 10 years ago in our school in math, where we started looking at data, computing the mean, computing different things. Maybe you learned a few more details last time with the percentiles and the median and the quartiles, which you may have not been taught in detail before, maybe you had. Anyway, today we're going to dig into probability for a few lectures. Why probability? Well, probability is important for us to be able to do the core business of statistics. Statistics is looking at numbers, or to be more specific, statistics is extracting information from numbers. And in the extraction process, we need probability thinking to be real intelligent about it. And that's the whole deal of it. That's the whole issue of it. So we're going to dig a little bit into the probability part of it. It's not a probability course. We do have another course, a splendid course, 2405, on probability theory, which you can take to learn more about the probability parts. But we need a little bit here in this course. Now, probability is a whole sort of area, scientific and applied area in its own right. Not specifically to do with statistics as such. Probability, it's the theory of games, the theory of the different randomness. And of course, this is an important field in many contexts, to be able to work with probability-based or random-based models, to be able to learn about and know about things. For instance, probability is clearly a key thing in playing lotto. That's the modern game, right? I have a couple of links in this collection. One of them is from the Danish Danske Spil, which is the main provider of games in Denmark. They had some problems with their online games, actually. Some of my colleagues are helping them now to actually monitor their games like you would monitor a production line in an industrial production line to make sure things are okay. Even though things were supposed to be okay in how they generate things randomly in their computers, maybe someone did an implementation error, which was the case actually previously. You can read the story. So you can use statistical methods to monitor actually what's going on. That's not the concept of today. There was a Canadian statistician. This is a long story. I'm just going to introduce it in a few words, and then you can dig into the story. This is a typical statistician. Small guy, a bit introvert. Extremely intelligent. What's that? Oh, I forgot the administrator thing again. Yes. How's the mood today? Great. Until started talking, it seems okay. I'll just accept like this. So this is the meeting room where you can log on if you feel like it to be part of this. I need to find the attendee list. I need to find Jeppe. I need to make Jeppe a host, right? There you go. Now what this statistician thought was, as statisticians, we think about numbers constantly, right? That's the life of a statistician. You look at numbers, you think about them, and you think, is it really random or is it not random? Randomness is one of the gifts of God to enjoy when you walk around and see random things happen. Then again, you might start wondering, this is one of, to the left here, my right, we have one of those many games that you can buy. This was in Canada for a few years ago. Nowadays, you can buy them everywhere. And you would scratch the numbers, and then you would see, these are like board games, and then you would scratch the numbers over there, and you'll see if you had 3 in a row. And if you had 3 in a row, you would win a prize. So, what this guy thought, I bet it's difficult to make those coupons with completely random sets of numbers and still be able to maintain the average payout and to make sure that they can control. And even, how do they do it? They have to automate some machine, some printing machine. They have to use a computer. They have to make some software to make this run. And are they really on top of all the randomness and making sure things are done okay? I know this is difficult, so maybe they are not on top of it. So that's what he thought. And then he had, the story doesn't tell how he came up with the idea, but apparently his brain is pretty okay. But the idea is pretty simple. When you see this thing here, this is what you can see when you stand in the shop. Then you can start counting. Like, for instance, here we have a row saying 24, 12, 29. You would see, is 24 anywhere else on this sheet? So he counts the number of times that the 24 is there. I mean, this is just some rule. I mean, where would it come from? But he thought, let me try playing around with these numbers. Maybe looking at some of the things that I bought that actually paid out a price to me. And see what is the structure? Is there a pattern in the numbers that deviates from randomness? And if I can identify this pattern, I'm up and running, right? Then he identified, whoa, this was a price, and the price, the thing that gave the price was these 3 ones in a row here, saying that the numbers 24, 12, and 29 only occurred once on the coupon. So that's what he calls singletons. If you then count all the numbers that appear only once, or count, you could do that just by looking at it, and you have a few minutes. You can look at it, and you see, if you find 3 in a row that are singletons, it's a payout coupon. And he found out that that rule worked in 90% of cases. So actually, he thought, I'm gonna be rich, right? I don't want to do statistics anymore. I want to be rich. But then he started. Then he started doing it, and he started evaluating how long time it took him to actually walk around in the kiosks and look at these and find out which pays out. And he thought, and also, I mean, not all of them pays the big price. Many of them pay small prices. So he calculated what the outcome would be compared to the time he would spend. And he thought, I'd rather be a medium-paid statistician in my life rather than walking around kiosks and doing this all my life. So he thought, I'm going to tell the companies that something is wrong. And they didn't want to listen to him. Think about the implications here. It's a huge mega industry, this game industry. And if they are caught with their trousers down, that's not good business. And you could have other, you can read the story, you could have other more, dramatic suspicions about if some of these games are really frauded. Is it by chance, or is it actually some more criminal activity behind that games are frauded? If you know there is a frauded game, it's easy to launder money, for instance. So there are many thoughts, and definitely the companies don't want to be on the front page. So they didn't want to listen to him. And then read the story. He bought 20 of the coupons. He put them into 2 groups in each of there. Then he sent this letter to the companies, and here are 2 by 10 coupons. Try to scratch them and see what happens. And then 10 out of 10 gave a price in one, and I think there was one miss, but 19 out of 20 was okay. And the day after, they shut down the game because they could see. I mean, how could you do that? I mean, put 2 by 10 if you didn't, without actually scratching them. That's a nice story that makes you think. This is a story about randomness and variabilities and probability theory. And that is the story of today. The first part of the story, we're going to make it into two actually three, but there are two chapters on this. Chapter 4 and chapter 5. One on discrete distributions, one on continuous distributions. So discreteness is when something can be counted, you could say. And continuous, that's when we observe continuous systems out there, like weight or height or the concentrations of something. So it reflects two different things, and we need two different kinds of math to be able to deal with this. That's why we distinguish between those two groups. So the agenda for today that I already started is the intro, where I would also discuss random variables, stochastic variables. We are going to look into some specific. We're gonna start rather abstract, actually, and then we're going to work us into the specifics. And then we have more specific things that some of these things you may know. For instance, the binomial. Probably you've at least heard about it, if not even actually worked with it previously. Then we are going a bit more abstract, and then throughout we're going to look at R, how to do it in R. So that's what we're going to do today. Stochastic variables, random variables, and their distributions. This is sort of the abstract, the sort of framework, you could say kind of a model way of talking about randomness. We're going to need some math and some formality. It's not going to play a major role, the formality, but it's also to just tell you that there is a formal framework system for dealing with this, mathematical framework. One of the things that we focus on are so-called stochastic or random variables, stochastiske variabler in Danish. We usually use capital letters to denote those. Loosely speaking, a random variable, a stochastic variable, I use these words interchangeably, is simply something that attains different values at different times. That's a loose. You could define that as a mathematical function, but we're not going to dig into this detailed formality. It's just something that sometimes gets one value and sometimes another value. For instance, one throw with a coin, right? Sometimes it's the tails, sometimes it's the heads. Two possible outcomes. Sometimes it's one, sometimes it's the other. The actual outcome is what we call a random variable, stochastic variable. Small letters are used for the actual outcomes. We distinguish, as I already indicated, between the discrete world and the continuous world here. The discrete world is what we're focusing on today. For instance, one throw with a coin, that's definitely discrete because the outcome is only two options, 0 or 1. Right? Very discrete. It's exactly the mathematical definition of discreteness, if you met this in a math course, that we are using here also. It could also be like 10 throws with a coin, and we count how many tails would there be. So that would be 11 possible outcomes, right? So you count 0 up to 10. Could also be counting the number of bacteria colonies in a petri dish that you sort of kept in a store, in an experiment in the lab. That could be a pretty large number. It could be like hundreds or thousands or millions. But that's also discrete, even though we get close to an area where there in practice can be like a sort of a gray zone area between what we call discrete and what we call continuous. Anyway, the one little thing, one out of two small things from chapter 3, which I didn't announce as real reading stuff. Anyway, I announced a little bit from chapter 3, but one thing is this sort of rather vague definition of probability, you could say, depending on how formal you want to be about it. The classical definition, we think of probabilities here as sort of frequential things, a frequentist interpretation of probabilities. And if we can count the number of possible outcomes, and they're all equally likely to, and we can count what corresponds to the number of, you could say, favorable outcomes in relation to the event that we are looking at, then the probability of the event would be given by the number s divided by the number n. It's a rather vague way of saying it. We'll be a bit more specific down the lecture today. Now, still I said the first part here is the more abstract part, actually, of the whole thing. There is a general framework for talking about probabilities, so-called discrete probabilities. Probabilities for a system. Now, we should think of a random variable in a way is supposed to be maybe modeling some system. The system could be one throw with a coin. The system could be 10 throws with a dice. The system could be the number of the number of hits on a website during 24 hours. There are many different sort of definitions of what a real-life system could be, but something that changes from time to time, right? The thing is, if we know the probability, I mean, a random system cannot be sort of deterministically controlled. We don't get full information of the random system by knowing what it will be in the future. But the thing is, we get full information of a random system by knowing the probabilities. So the probabilities are the key issue, the probabilities of all possible outcomes. That's the key to complete information. We want to know the probabilities. So we have a name for the probabilities in a system. And the probabilities in a system is actually called the density function, small f. Here is the formal definition of sum. It's just to say there could be infinitely many different probability systems out there. There is a formal way of defining what is a probability system. This is a system where we have defined by the individual probabilities, which makes sense in a discrete world, because we have discrete acts. We can point out all the possible outcomes in the system. All the probabilities should be either strictly positive, or they could be zero. Some outcomes could have zero probabilities, but definitely the sum of all probabilities should sum up to 1 for it to be a meaningful probability system, so to say. That's a density function. There's another function that tells a story about the whole system. If you know the density function, you know everything, as much as you can know in a system. That's the same goes for the probability distribution function. The distribution function is, two ways of writing the same thing, is the accumulated densities, that is the accumulated probabilities from whatever to the left, down from minus infinity. Many of those could be zero maybe, but at least from as far left as we can go, up to the point where we are in a way. So the left tail probabilities, you could say, of the system. The definition of the probability function is the probability of being less than or equal to the point. We will, of course, exemplify this a lot of times in a few minutes. Okay, this was actually the general part of the story, the abstract part. There can be a discrete system, random system. We have density function and distribution function to tell the story about these systems. So we end the first part here, George, and we go on to the second part.